Okay, we're live. So, hi everyone, we're here for another Science Sunday Hangout on air. This time we've got Yonatan talking to us, and he has a background in string theory, but I'll let him introduce himself so he can tell you all about what he used to do.
All right. So, hi everyone, I'm Yonatan Zunger. Oh,
I was just going to introduce you as well, but I'm Scott Lewis.
Yeah, sorry.
I am the producer in the Education Public Outreach team at CosmoQuest. This is another one of the December broadcasts going on for the entire 12th month of the year 2012. It is a Girl Start initiative, and this year they partnered up with Google Science Fair in order to help get everyone involved in science, technology, engineering, mathematics. And we do have Yonatan here today to give us another branch of the STEM fields and all the different applications that can be done with it.
all right. So, hi, I'm Yonatan Zunger. Once upon a time, I was a string theorist. I started out in that field. I did research on the fairly mathematical edge of string theory, which is a rather alarming thing for those of you who know string theory, but studying the basic nature of space-time and what happens when space-time itself breaks down into something or other beyond that we don't really understand. I did my PhD at Stanford, hit a very serious case of being sick of academia, and decided to switch over from physics into engineering. So moved over to Google, where I've been working on things like artificial intelligence, systems infrastructure, search, a lot of problems like that, and nowadays I'm on Google+. And so I'm here to talk about science, technology, engineering, and mathematics in any order that you want.
That is quite the transition from string theory to engineering to Google. I mean, it's such a great way. Is there something that really got you interested in science from a really young age, or?
I grew up with science in the house. My dad is a physicist. He still beats me for searches for our last names on Google, because his papers have such a high citation index. But so we definitely grew up with science very much in the house. Although I took a very different direction from him. He's a condensed matter physicist, very focused on applications, on things that can sort of directly transition from the theory paper into the lab, into practical applications, into industry, into the world. Whereas my own physics interests shifted quickly towards, let's understand the most fundamental laws of the universe and see what the universe is actually doing.
Right. I'd say that's a big difference. And could you give us a brief, I guess, bite-sized bit of what string theory really is, or how you would best describe what string theory is? Because a lot of people hear it, they've seen the Brian Greene documentaries on PBS, but what to you is string theory to allow the general public to best understand it?
Okay, so basically, string theory is part of our attempt to understand what are the most basic laws of nature. I mean, how is the universe, what are the laws that actually control how the universe works? So we're not trying to study the very complex high-level phenomena, not like how do atoms form molecules, how do molecules form life, or anything like that. We're trying to ask, what are protons made out of, and how does that tick? And the problem is, the big challenge, is that we have two great theories of nature, each of which explains part of nature, and which work together really poorly. Right? So one of these two theories is called the Standard Model. And this is the theory, this includes quantum mechanics, quantum field theory, electrodynamics. It explains all of the nuclear interactions. That's everything from the structure of protons to how fission happens to how stars burn, all of this stuff. And this is what we probe in particle accelerators too. And the thing about that theory is it's amazingly effective. It's the best predicting physical theory that humans have ever made. We can predict some things like the response of an electron to a magnetic field to 14 decimal places, and measure it to 14 decimal places, and they match. That's insane. That happens nowhere in the universe. And this explains three of the four known forces of nature. It explains electromagnetism and the strong and weak nuclear forces. And basically, the strong force is what holds nuclei together, and the weak force is something that has to do with how nuclei fall apart. The other force of nature is gravity, and we have a great theory of gravity too. It's the general theory of relativity. Einstein came up with this in the 1910s mostly, and it explains gravity as beautifully as the Standard Model explains everything else. It explains how stars form, how galaxies move, how the large-scale structure of the universe gets shaped, and again, it does an amazing job. And the only problem is that these two theories are completely incompatible with one another.
Right.
And when I say completely incompatible, it's kind of a disaster. So you can say, I want to study the standard model in the vicinity of the gravitational field. That works out. It works great. But if you ever have a situation where the particles of the standard model are creating enough gravity to actually affect what's going on. So if you actually want to study how standard model particles create gravity in the first place, everything collapses. The entire theory falls apart. And it's not like the delicate, like it makes bad predictions.
Right.
It's things like, if you ask it, what is the gravitational field of a proton, the answer is infinite.
Infinity, right.
So it's a pretty catastrophic failure. And it turned out, what we discovered over the 1960s, 70s, 80s, was that this was actually a very fundamental thing about theories of particles. It turns out that owing to some mathematical aspects of the way that general relativity works, if you try to make it play nicely with any theory that involves quantum mechanics and particles, it will break down in this way. You can actually prove that mathematically, that it will never work. And so then by a bit of sheer chance and luck, someone hit upon the idea of saying, well, what if instead of particles, you looked at little strings? So imagine you have like a little loop of some basic string matter, and that little loop can fly around and so on, and it can vibrate and twist and turn and so on and so on. Now, if you look at this loop from far enough away, it looks like a particle. But if you look at it from really close up, it is very definitely not a particle, and it interacts in very different ways. And what turns out is there's this absolute bit of magic that if you try to write down an equation to describe the motion of a string, that obeys the basic rules of quantum mechanics and of special relativity, which is sort of this simple, here's the basic way that geometry works when you have space and time, not the full general theory of gravity. It turns out that you have only 6 different consistent equations that you can write, and it's basically one equation with a couple of choices you can make in it. This equation describes strings moving around. It turns out that these equations, in fact, predict the entire general theory of relativity as a side effect, because these strings will proceed to interact with each other in a way that looks exactly as though they are bending space. It turns out that if you let them bounce off each other in various other ways, they will interact in ways that look an awful lot like the standard model, although there are a number of details which vary, and that's part of the hard part. And just in general, you have a theory that seems to describe a huge fraction of everything and resolves both of them. That theory is like classical string theory. That's the theory that we worked out a lot especially in the 80s, going into the early 90s. And since then, Jose has had a number of major upgrades. But basically, it's one of our best attempts right now to understand the basic nature of the universe.
Right. So I've heard many times, as many of the public here has, of a unifying theory to take our ideas of very large, massive objects, and then taking our understanding very small, the atomic, subatomic level. And so string theory is finding a way to explain both without everything being infinitely massive at the same time.
Exactly. And that also, therefore, lets us explain extreme situations like what happens in the center of a black hole, or what did the universe look like in its first few instants of creation. Very
good. So it's really complicated, and it's really amazing. I mean, complicated is like saying that telling a first grader to start doing differential equations. It's kind of complicated, but what helps us actually understand what everything is doing, how everything is doing it, and helps us actually predict these higher levels as we go up through the structure. So we are able to do chemistry, we are able to do actually the other physics, we're able to do biology at a much more precise way of just understanding what's going on. So with this theory, this string theory, or the different variations of it, we're able to do better science throughout all the different fields. Would you agree with that?
Absolutely. I think that's exactly it.
I know Houdini doesn't really do too much with string theory in her lab, but I think what helps is when you have the different theories going on throughout history, throughout mankind, and watching them evolve, we see the ripple effect throughout all the different fields going on. And so if we can get a better understanding of the tiny things that are happening, and if we have a better intimate knowledge of the cosmos and of the universe, of what's actually happening with it, we can have better applications 20, 30 years on the line, hopefully, as that's going on. Now, do you think that there's any limitations with that field? of research in string theory that we're having to come up against?
Yes. Unfortunately, string theory has hit a couple of... It's basically, there's two different brick walls that string theory has been running into. One of them is mathematical, the other is experimental. The experimental side is that the string theory makes a lot of predictions about, it's predicting that you will have a standard model of gravity and so on. We can study that. But the first places where string theory starts to really radically deviate from the stuff that we already know about the standard model happens at very high energies, which you basically can't produce in a lab. So we're left to try to find other ways to probe the experimental reality. I mean, is string theory right? We don't actually know. I'd be willing to bet some pretty solid money that it is, because we seem to find that it's pretty much the only consistent way to pull various things together. But to actually really probe that requires energies that we can't produce. So we have to instead do things like do astrophysical observations and look at the remnant radiation of the early universe, because nature thoughtfully provided us a giant explosion at incredibly high energies.
And I'm down with astrophysics, so more astrophysics. Yay.
More astrophysics. There's a lot of astrophysics, interplay between astrophysics and string theory nowadays.
Right.
And the other hard side is mathematics. When you said that it's just a little bit complicated, it's worse than that. Sometime around the late 90s, I'd say, we started to really run into the brick wall of the mathematics simply isn't advanced enough to do string theory yet. When I look at my own research, I was out there writing papers that were basically math papers. And I'm proving new theorems. I'm out there giving seminars in math departments telling them, hey, look, I found a way to deal with non-abelian gerbs. And they say, really? We've been trying to figure that out for a while, and we couldn't think of the right way. I said, yeah, well, I just sort of needed something, so I hacked it together. And it seems to kind of work. Which is actually, historically, half the time math is ahead of physics, and the rest of the time physics is ahead of math.
Right. And
we seem to be entering one of those phases where physics is running ahead of math and just sort of developing its own math as it goes along. But I can't remember who it was who said this, but someone once described string theory as a piece of 25th century science that fell into the 20th century by now.
There you go.
That's very definitely the case.
Right. Now, and just so everyone knows, we will be checking the comments as we're going through. I'm going to try to not ask any questions to help better explain all of string theory, because this is supposed to be a general conversation. I'm sure that we might be able to have some discussions offline or some comments that can be responded later on. But if we have any questions from Yonatan here about his career, what actually brought him throughout all of his steps through academia and now into the private sector, please feel free to comment on the event page, on any of the shares on Google+. On Twitter, we're using the hashtag #December, and also we have the YouTube. So if anyone out there is watching on YouTube, we can track those comments there, and we will field those questions as we can.
So starting with one of the questions, we have a really interesting question from Gaithia, and she's asking Yonatan's transition from academic physics to Google and what connections he may or may not see between the quest of physicists for a unified field theory and Google's development of internet searchable knowledge base and human communications development. Do you think there is an overlap between the grand theory of everything and Google?
That is a good question.
Yeah.
I think that the overlap is in attitude. In string theory, we're trying to find a theory that pulls together the whole world. We're trying. It's as ambitious as it can possibly get within the scope of physics. It's like there's never any well, we explain 90% of the world. That's not enough. There's a whole 10% out there. And I think there's something very similar in the Google attitude of, you want a system that's complete magic, that makes the sum total of all human knowledge available to you just as part of your day-to-day thinking process. It's a pretty crazy sort of thing. Actually, one of the things that drew me into Google in the first place was when I had a meeting with some people at Google, and they sort of hinted about this crazy idea they had to scan all the books in the world and make them accessible. And I remember going home and thinking about that and thinking, that's the most amazing idea I've heard of in years. Imagine what would happen. And actually, the next day, I sent in an application just because of that sort of overlap.
That is awesome. I think it's really important to be able to have that information available to everyone, especially with books. Books are phenomenal. Books are a way that we've been able to connect to cultures, from centuries and centuries ago. That's why we were able to know about the Greeks, is because they wrote things down, and we've been able to read them, 2,000 years later. And I think it's absolutely wonderful. So finding a way to transition now that we're in a digital age, I think is absolutely a great reason to get involved with the company of, hey, we're trying to find a way to get all the written information down in a way that it's not only cataloged, but people can search it readily. That's actually wonderful. Now, you said that you grew up in a home where science was very much a part of your life. Is there something that made you fall in love with physics as opposed to any of the other fields going on? Or is it just because your father already works in physics and that was kind of just expected along the line?
Actually, it was almost the opposite. I think my father working in physics almost caused me to not work in physics. But what really pulled me, it was the same sort of thing. I was the kid who kept asking why, and I was never really satisfied with any particular stopping point. And I think I grew up to be the sort of adult who keeps asking why, can we generalize this? Is there something more fundamental?
Right.
And that's what pulled me not just into physics, but into string theory in particular.
Well, no, go ahead, Yonatan.
No, I actually tried to work in other fields. I spent a couple of months trying to work in solar physics when I was early in grad school to see if I could enjoy that. And I thought, this is magical, but it's not as magical as string theory. I'm not getting to answer the basic questions.
Well, I know my friend Dr. Thad Szabo is out there watching this, and he did study the sun. He was the solar astronomer, but there are so many wonderful, amazing questions to be asked out there. It's difficult to choose just one, but I think you hit the point on the head. That's been a really common theme throughout all the different December is curiosity and pursuing your own curiosity. Being brave enough to ask questions. Being brave enough to say, I don't know and I might not find out, but let's try anyway.
Yes.
And I think that's a huge key component with many of the different scientists that I've worked with and been able to interview, is that that curiosity is key. No matter where you're coming from, you can find those resources to help you answer those questions. And sometimes you need to hack your own and make your own resources to get yourself there. Like you're saying with the mathematics. So, well, I don't have the math yet, so let's figure something out. But I believe some other famous scientist did something like that a long time ago about making his own math. I don't know if anyone knows who that is out there, but I think it's a brilliant way of approaching it, that sometimes you do need to think outside the metaphorical box and find different ways of explaining something that we don't have the tools to do yet.
Mm-hmm. And by the way, part of why I'm laughing is that although I know who you were talking about, there's actually a lot of scientists who did that. Pretty much, I'd say something like 60% of the mathematics of the 19th century was actually invented by scientists who said, damn it, I need a better tool.
Right.
So, and not just mathematics. We have, the reason that we have, rubber soles on our shoes and fascinating artificial teeth and so on, a lot of this comes out of crazy stuff NASA was doing because they needed a better tool.
Right. And it's just a perfect way of being a hacker. You have to find a way to make something work, and sometimes you only have duct tape. And what am I going to do with what's around me and duct tape to make it, make this utilitarian? And you do it. And then you can make it prettier later on. You'll have to go through and work it out. But sometimes you just need to find a tool to do the job. And it's not necessarily pretty the first time you do it. Or sometimes it is. But it's...
So MacGyver, scientist.
MacGyver, yes.
Yeah.
Yes.
When I was an undergrad, I had to build basically a small cosmic ray observatory out of spare parts. And pretty it was not, but it was very effective. It looked like a mass of junk piled on a couple of tables, basically.
That's awesome. Now, I see a question here. It's from Kelvin Matthias. Would you recommend an undergraduate student to pursue a PhD in string theory?
Yeah, okay. No, I'm required to give this statement. If you can find any other field that you want to work in, you should work in that field. The reason I'm saying this is because this is a brutally hard field to be in. It's not just that it's demanding; it's that you will have to maneuver not only the physics and the mathematics, but the people, the politics. Academia is not a simple field to be in. If by any means you cannot do physics, then you should not do physics. And pretty much the only reason you should do physics as a career is if you look at it and you realize that no, you have to do physics. Like you are going insane when you're not doing it. You are bashing your head against it. You are clawing against the walls. The sciences are like art. If you want to make this your career, you have to want it more than anything else in your life. You have to want it more than
Right.
And
So
if
it's
you
not
do
for
want,
the faint-hearted.
it's yes. The sciences and the arts do not do this unless you mean it. On the other hand, if you do mean it, if this is something which is that important to you, then there is nothing more rewarding for you. It is something that you will die feeling that your life has had to or haven't done so.
And I think that's very accurate as far as the point that most scientists I've met and I know personally that passion within them is not something that just dies. It's not a passing interest. They don't get into this field because they're like, yeah, well, space is kind of cool, so let's go learn what's happening out there. And I did all the math, so now I understand what's happening on with nucleosynthesis. But hey, it's definitely with all the different fields that you have that passion within you. It consumes your life, and it's the way you're allowed to be happy by better understanding for yourself, and when you're publishing, you help explaining that to somebody else as well. I think that's a huge crucial thing, that communication involved as well.
Scientists don't retire. This is the sort of thing that if you're doing it, you're going to do it until the day you drop.
And some do, up until the point. It tends to be how. When Einstein was in his deathbed, he was still trying to formulate a unifying theory. He was still going over it, and it's very common that you're never out of the lab. You might be physically out of the lab. You might be physically out of the university. You're not in your office anymore, but you're always thinking. You're always formulating something going on, trying to have a better understanding of what's going on around you. That curiosity consumes.
Yeah, and one of my favorite things about being a theorist was that you really didn't have to be physically in the lab or anywhere. You could be on an airplane, you could be imprisoned in Siberia, and you're still sitting around and doing physics.
Right. Now, I'm seeing another comment here from Gary Ray. Do you have any metaphors or teaching aids to help explain strings or brain theory, and why Planck lengths limit us, the Planck lengths? And
also, what is brain theory?
Okay, well, that's a good couple of questions. So let me start with the top one. What is brain theory? That's basically an upgrade to string theory from the mid-90s on.
You can say 42 if it makes it easier to explain.
No, in string theory it's 26, not 42.
Hey, right. No inside jokes between astrophysics people. The biologist demands that.
That's geeks. I can actually turn that into a Kabbalah joke too. But anyway, I'm equipped for any sort of bizarre conversation. Very roughly, I said there were 6 different ways to write out the equations of string theory. Turns out that one of those 6 ways doesn't actually describe the universe much at all. The other 5 do, and these were called the 5 string theories. They have the wonderful names of type 1, type 2a, type 2b, heterotic O32, and heterotic E8 cross E8. I am not going to try to explain what those names are, but you will be quizzed on them shortly. And one of the important things we discovered in the mid-90s was that these 5 things that look like 5 different kinds of string theory were actually just 5 different limits of some single underlying theory, a deeper theory, which seems to be a theory of 2-dimensional membranes, not of strings. And again, if you look far enough away, like the membranes might twist themselves into a very thin donut that looks like a string, and if you look even farther away, it looks like a particle. So we have this whole theory of membranes. It's been called M theory. There have been jokes about M standing for membrane, mystery, magic. I can't remember who it was, but someone at one point stood up in a conference and called it the mother of all theories. M theory is our current best hack at the fundamental underlying theory of the universe, and we don't understand it very well. Now, in string theory, I can write down for you the basic equations of string theory. I cannot write down for you the basic equations of M theory. We just don't know what they are.
Okay.
Now, the next question was about metaphors, huh?
Yeah, you're getting down to the Planck lengths. We're talking about tiny, way beyond anything we can even imagine, or at least most people can imagine. Are there any sort of visual representations for what's happening here to propagate what these particles are? So
I think there are a number of metaphors for different things. Like I have a good metaphor for general relativity. I have a good metaphor for extra dimensions. If you want a good metaphor for the interactions of strings themselves, then actually the best thing is to use the actual diagrams that depict this. And since I don't have a blackboard here, wait a moment, I do have a whiteboard here. What am I thinking? How awesome. Let me see if I can actually draw something.
Yes.
Okay. I don't know if you can see this. Let me try to draw axes just so I can see what's on the screen.
It looks great. Yep.
Okay. So let's say the time goes upwards and this is like space. Right, I'm drawing only one space dimension because this board is flat. So here's a string, and here's another string. So you can imagine it's like stretched out in. This isn't meant to be extending in time. I just can't draw a circle very easily. And so this string is merrily moving its way along through time. So it sort of traces out a cylinder in space-time. So that's called the world sheet of the string. Right? If it were a particle, it would be tracing out a line instead. But we don't have particles. Sorry. And here is another string. And these two strings, maybe they're going to merge to form a bigger string, so then we get to test my artistic ability. And you get a pair of pants. So here's an interaction where two strings merge to form one bigger string. And then, maybe later on you'll see the same process in reverse. That string might split off into two different strings. This is what sort of the basic interactions of strings look like. They merge with each other, they split, they join. Now, the actual mathematics of that splitting and joining are rather subtle. And the reason is because the strings aren't simply moving in a straight line, they're also vibrating. They're vibrating and shifting around, moving in space. And when you actually take into account, basically what happens is if you look at this string from very far away, all the different patterns of vibration within the string look like different particles to us from a distance. And on top of that, if space-time is actually not flat, if space-time is curled up in various ways, then these things can wrap themselves around the structure, the universe itself, basically. And that gives you even more kinds of particles. And I can give you metaphors for that if you want. And it's by actually understanding the mathematics of those interactions that you derive things like the standard model general relativity, and so on and so on.
I bet you wish you were an astronomer, because you just have globes up right now and just playing with things, right?
Yes, that would be so awesome.
So it's basically a Jordache theory with those pants, and then when they vibrate, it's hot pants. Is that what's happening?
Yeah, pretty much.
Okay.
Pretty much.
I get it.
Yeah, we also have open strings, by the way, that look like little line segments instead of loops. And they do pretty much the same sort of thing.
So I hope that helps a little bit there. Gary, I hope that helped understand a little bit. But like we said, we're not going to try to go too deep into what string theory is in this broadcast because you're not getting paid to do this, and people take expensive classes to learn that. But I think this is going to be more...
I'm totally happy talking about actual physics in this Hangout, not just about like why physics is cool.
Right. Now, we do have another comment here. Do you see Ishika there, Padini?
Yeah. Let me scroll down. Yeah. Okay, I've got it up there.
So I'm a 13-year-old, but I understand technical language and things like string theory. I want to get a PhD in physics when I grow up. I love string theory.
Excellent.
Very good. I think we need more 13-year-olds out there trying to have a better grasp of just the fundamental anything that's going on.
Yes, you should. And if you're that excited about string theory when you're 13, then you're doing it right.
You were definitely doing it right.
Then you should, by all means, keep studying it, go off, do a degree, learn about this field, come and love this field.
Yes. Or any field for that matter. I mean, string theory and any of the physics. I love physics. I live.
Dude, what are you talking about? String theory is obviously better than every other kind of physics.
It's true. I mean, it's the mother of all theories, right? But that's when we have a biologist here to call us both dumb because she can't see what we're talking about. And
yes, and she's going to wave tentacles in our general direction.
Hey, squid, they're gonna take over the world.
Those damn cephalopods.
It's true. Let's see here. Well, I have a question here from Amber Pecci. I hope I pronounced that right, Amber. So what is one tool you would not do without? And you can't say computer or pen, but what's something that you personally could not do without?
Are we talking about a tool for doing string theory, you think, or a tool for...
let's keep it to any of the STEM for you growing up. What's something that you've kept with you the entire time that really has really helped? I mean, I'm going to say that a calculator counts as a computer because technically a computer is a really strong calculator.
Although actually, I wouldn't even say a calculator. I mean, when I was doing string theory, what was the tool I could not function without? Pen and paper. I mean, I had notebooks. I was insanely picky about my notebooks and like the quality of paper and the pen and so on because I spent, most of my day sitting there scribbling. I didn't actually use computers that much. There were only a handful of calculations where computers would be any use at all. Mm-hmm. I would be more likely to use an integral table than Mathematica, actually, for which I recommend Grajstein and Rijik, whatever the most recent edition is. Yeah, actually, pretty much the main tool that you use when you're doing theoretical physics is your brain. It's not anything external to you.
Right.
And nowadays, as a functioning computer scientist, then the actual, the tool chain that I actually use in my day-to-day life right now is also pretty simple. I use a web browser because I develop web apps. I use a C compiler, a nice distributed C compiling environment, and I use VI. I'm not much for fancy tools.
No.
No. I tend towards the very simple, like one good simple tool that just does exactly what you need.
So a sonic screwdriver, essentially. You just need something simple.
Yeah.
Actually, not kill anybody, but...
Well, I don't mind if it kills someone. I'm okay with other sonic devices too.
I think the simplest and most complex at the same time was what you said, your brain.
Right. Was there anything that you did to help, just doing some brain tests or some brain games growing up that helped you hone your ability to think mathematically or even think with abstract maths in your head? Because I know a lot of times taking the actual maths of writing it down and having it formulate in your head is a big change from being able to do that. Is there anything that helped you develop the abstract maths inside your head?
Wow, that's an interesting question. My intuitive answer to that is the way I developed the ability to do abstract math was by doing more and more abstract math. I definitely would develop my own ways of visualizing mathematics. And I think everyone who does mathematics has to do that, right? I mean, how do you visualize complicated math structures like fiber bundles or eigenvector decompositions of million-dimensional matrices? It's because you've played with them and you have some. You have some kind of mental picture, but really you get better at this by practice.
Right.
It's just simple practice, and if it's not the sort of thing where the practice itself makes you happy, then again, this probably isn't what you want to be doing with your time.
Well, I think that's a good point for any sort of maths. Is the only way to get good at maths, and especially it goes further into science, is the only way to get good at it is that you practice it, because you start seeing those patterns because you're repeating yourself, and you might have different values, but it's the same process going through, and you become familiar with what's happening, and you're able to build on top of it.
Not quite different. A lot of the homework they give you in elementary school for math is, I think, the most useless homework ever.
Right.
It's like, let's do addition 50 times, not 50 times, several hundred times.
Right.
With just different numbers. It's useful the first couple of times. After a while, if you haven't gotten it, it's not going to. That's not the way you're going to learn it.
Right.
And similarly, they give you these word problems that are just obviously fake ways to get you to do a computation.
Right.
I mean, if you want to learn math, you should do math. If you want to learn physics, you look around at phenomena around you and try to understand what's going on.
Absolutely. There's something I did with my students this semester was we had discussions for the first session of the week, and in the second session, that's when we actually did the math. So we went and had them discuss one part from what we were supposed to be, and have them debate over why it's happening. We'll go into the math later, and you can prove each other right or wrong. Mm. But once you get into the practice of trying to conceptualize what's happening, the math is just explaining why your concept makes sense or not. And then you start tying in that math that you know beforehand. Well, I know because this math I did 10 steps ago is right. You're able to go from there. So I think you're absolutely being able to visualize these concepts happening, which is not necessarily a natural thing to everyone. Sometimes you do have to learn how to think that way. But I know for me personally, I had to develop that within myself to be able to think that way. But it's amazing.
You definitely have to learn. I don't think this comes automatically to anybody.
Right.
I mean, if I had to actually summarize, like, what is the purpose of any class in physics? It's what you're trying to learn is to be able to describe physical phenomena involving blank, and that blank is different for every class you take, and explain what's going on and construct a mathematical model that seems to describe it.
Right.
Or construct a model, period. And math is just a tool that it happens to work pretty well for that. But you have to learn that. I mean, that's what you're learning, is how do you look at a physical thing, chop it up into its basic parts, figure out what's salient and what isn't, and just pull out, like, here's what's actually going on in this picture.
Absolutely.
And part of trying to relate that is by having people like you speak about it and kindle that, fire of curiosity. And also popular science books and things like that. And going from that, there's a question we have from Benjamin. He says he wanted to learn a little bit about string theory and ended up reading both Not Even Wrong, The Failure of String Theory, and The Search for Unity in Physical Laws by Peter Voigt, and The Trouble with Physics by Lee Smolin.
Oh, no.
Obviously, I would end up with a bleak view of string theory with only those books to inform me.
Oh.
What can you say to a layman regarding the untestability of string theory? Has our understanding changed much during the publication of those books? If those are the only books I have read on the subject, what am I missing? What other books would you recommend to get a broader understanding of string theory?
Okay, so first of all, the answer to what you are missing, if you only read those books, is string theory. Okay, I need to branch off and explain a bit of the meta here. If all you read is those two books, then you are wading into the middle of a giant pissing contest. And it's a mass of complicated academic politics and so on and so on, and this is so not the place you want to start, because you're getting in the middle of some controversy that was not going to make sense to anyone. So here's the backstory. There is another theory that is trying to unify all of these forces of nature. It's called loop quantum gravity. And the number of practitioners of loop quantum gravity is, I would say, much smaller than string theory. I'd say it's a few percent only of the size. That theory has different pros and cons than string theory. It seems to be better at describing phenomena when there are very strong interactions at play, and it is worse at describing phenomena when the interactions are relatively weak. These are very technical sorts of differences. Now, I think that most people in the field, people who don't personally have a horse in this race, tend to believe that ultimately both theories are going to be right, that the actual underlying theory, whatever it is going to have both our current understanding of string theory and our current understanding of loop quantum gravity as sort of special case limits of the big underlying theory, whatever it turns out to be, because they both seem to whatever extent they do work, they both seem to work, and it's pretty likely that if they both work, that they're just two limits of the same thing. That seems to be how it happens in fundamental physics. However, there are people, and Lee Smolin would be, I would say, the king of those, who definitely have a horse in that race. Highly, if you're out there. And there is an enormous pissing contest going on about, no, string theory never predicts anything, loop quantum gravity is the only one that is right. On the other hand, you have loop quantum gravity can't even make predictions, that's why its predictions are never wrong. You people are wasting your time. And if you read these books, you're going to basically be seeing a snapshot of that pissing contest, not of any actual physics. So I would suggest that if you want to actually get an intro into the world of string theory today, Brian Greene's book, The Elegant Universe, is not a bad place to start. I believe Lisa Randall has some books, some general public books out as well. I would definitely give hers a look. I should say that both Brian and Lisa are actual practicing string theorists. They're not science educators, they're not journalists. They actually work day-to-day in the field. Brian Greene is known for his work on conifolds and a lot of these very subtle shape of space-time issues. Lisa is probably best known for her work on string cosmology and what's called the Randall-Sundrum lines. So these are very serious people, and they're good explainers, which is really important. So that's where I would start as far as finding out about strings.
Well, I think you bring up a good point, though, and something for people trying to get into any of the STEM fields is remember that there's people involved. And when you have people involved, things happen. And lots of nasty things can happen, too. And so to remind yourself that we are dealing with humans, and humans do make errors quite a lot. And then you do have spits, and you do have egos involved. And sometimes you will have a backlash. And so going into any of the STEM fields thinking that there's not going to be any of that because it's academia and there's this white ivory tower. No, there's a lot that goes on behind the scenes, and it's not to discourage anyone, but to make sure that they're aware that you will have to remain strong within yourself while also being strong within your maths and science going forward too.
Yes, I can't emphasize, you are so right about that. Something, every time I get new people in, not just in physics, but also in engineering, in any field, in STEM fields in particular, and I always get the people who seem to believe that if they're just good enough at technical aspects of their field, everyone will love them and they will succeed and they will never have to deal with people, and just their pure ability will solve all their problems. And then I have to break to them the true fact that that is in fact not the case. Sorry, you are in fact working with people. You have to be able to form collaborations. If you're working in science, you have to convince people about, it's not that you have to convince people that your ideas are right necessarily, although when you're working in purely theoretical fields, in fields where you don't have experiment to fall back on, that is actually an issue. But you have to convince people that the problems you're working on are the important problems, that these are relevant, that this particular method of pursuing the truth is the one that's going to bear fruit. When you're working in engineering, even more so, you have to actually build things that work, which requires building teams that work.
Right.
And man, people, there is a certain fraction of people who are, I mean, honestly, it breaks their heart when they discover that that's true, that their dream of not having to deal with people is just a pipe dream. So if that's what you're thinking, I'm sorry, STEM will not help you. You're going to have to learn people.
It's not like, it's not like just a bunch of lone scientists in a basement not having to deal with anyone. The grant money just keeps flowing in because no one's writing them. They just keep being refilled. But that's another thing that goes into too is finances, and you do have to play that game as well. There's politics in every field. And
you have to actively market your work by promoting it in conferences, by publishing it, dealing with people. It's not enough to do the science. You have to get the money to do the science, and the way you do that is by getting people enthused about it.
So being a good communicator does help. It does really help. If you can speak and interact with people and do science, it's phenomenal.
One of the most probably the most successful person in string theory today is Ed Witten. This man has been nicknamed the Pope of string theory, and he has a background in journalism. And that's actually been a huge part, I think, of his success, because you read some of his papers and everything seems so completely obvious, and you wonder, why didn't I think of this? It's not obvious. He's just good at explaining it. So yeah, communication is a really, really important skill. And as far as the rest, Kissinger said, the reason academic politics are so vicious is because the stakes are so small. He was right.
Yeah, it's true. I mean, it's sad, when it's put that way, because you're trying to understand the very nature of the cosmos, which seems like a really big deal to us because we think it is and we know it is. But convincing the rest of the world that do have their 9 to 5, that do have to have roofs over their head and food in their belly, that have many other things taking up their time, you have to convince these people to, hey, throw me some money because I'm working on this and I can't work a 9 to 5 job and try to understand the universe at the same time. Well, you can, but 28-hour days haven't been introduced yet, so yet.
Yet.
So one of the questions,
that's the string theory's department.
One of the questions I wanted to ask Yonatan is, what advice would you give to someone who's considering a career change from academia to industry? I mean, that's a path you went through yourself, and that was a crossroads you faced. What was your thought process, and what advice would you give to someone?
It's another very good question. I think the best advice I can give is the hardest things for people making the transition from academia to industry tends to be the shift on the focus towards actually getting things done. I'm thinking of a friend of mine, someone I worked with here. This is an academic. She was a very successful professor of computer science. She's a very brilliant woman. And she came here, and at first she had the hardest time succeeding because she was always trying to find a theoretically clean solution to this problem. And I would tell her, look, this solution might be theoretically clear. We don't have the time to work on that, and it's not worth the effort either. And I remember as she worked on this, one day she suddenly had that moment of insight. Now, actually, I think I got to be in the room when it happened, so it was really wonderful, of understanding that, you have a theoretically pure solution that will solve 100% of the problem. You have an extremely ugly and theoretically embarrassing solution that solves 90% of the problem, but takes 10% of the time. And the correct question then is that extra 10% worth it? What's in that 10%? And learning to make those trade-offs between theoretical purity and is this actually good enough to actually solve the problem at hand is, I think, the hardest thing for academics to get used to. And the thing is, the moment she understood that, she suddenly became hugely successful in this field because, a lot of the same skills that make you successful in academia do help. But I think that sort of attitude of let's find a way to get things done and simply understanding things for the sake of understanding things isn't what we're here for. That's the hardest jump for people to make when they move from one to the other.
Okay, thank you.
So real quick, we can just do a quick station identification, let everyone know who we are, what we're doing. This is the month of December, and so the Girl Start group out of Austin, Texas, which is a group that gets involved with young girls K through 12, trying to get them involved and excited about science and technology, engineering, mathematics. They've come to Google Plus this year and partnered up with Google Science Fair, trying to bring more awareness and celebrate how exciting all the different STEM fields are. So we've been hosting many different hangouts on air through Budini and I, but also with, say, CERN, we had Scientific American, the San Diego Zoo, AccuWeather.com. So there's many different activities going on throughout Google+. You can also go to december.org and take a look at their calendar to take a look at some of the recorded hangouts on air, plus any future events that are coming up. I'm Scott Lewis. I am the Hangout producer and on the Education and Public Outreach team for CosmoQuest.org. And Budini?
Yeah, I curate Science Sunday and also STEM Women on Google+. And yeah, my science outreach efforts are kind of secondary to me being an actual scientist. But it's fun and I love doing this. So thank you both of you for being on here with me.
So just to let everyone know, we're going to field questions for probably about another 5 minutes before we start wrapping it up here with Yonatan. So if you guys have any more questions, feel free to add them to the event page on Twitter using the hashtag December. On YouTube, we're checking those as well. And then any of the shares of the Hangout being done throughout Google+, we're able to actually check those reshares for their comments. So please feel to make questions, comments, tell Yonatan how great his hair is because... second of all, it's pretty awesome.
We have a question from Kuhn Depos. He's asking, is there still hope for SUSY, and can string theory survive without it? What are your views on the universality of computation? And Gödel's, is that how I pronounce
Gödel's incompleteness theorem?
Yes.
Boy,
the
okay. Well,
simulation hypothesis, the holographic principle, and yeah, he goes
so
on.
there's a lot of
but
questions.
you can interact
Maybe we
with
can
it.
take some of these one at a time. Okay.
Yeah.
The first one was about SUSY, which is a short for supersymmetry.
Right.
So there's no way I'm going to be able to give you a sufficiently short overview of supersymmetry itself, but very roughly, supersymmetry is something, it actually shows up even in the standard model, even before you're trying to deal with string theory. And it's a symmetry that we suspect exists. It's a very deep symmetry that actually relates different kinds of particles to one another and ties a lot of things in the universe. And the reason that we can't just look out the window and say, well, do we have this symmetry, is it turns out that this symmetry only manifests at high enough energies. Basically, at low energies, it's the same way that inside a magnet, like let's say you look inside an iron magnet, each atoms are spherical, basically. An atom on its own doesn't have a direction, but each atom has a little magnetic pole, and it's next to another atom with a magnetic pole, and they want to align themselves. So if you have a bunch of atoms, they end up picking a direction. And so when you look at a magnet, it's got a preferred direction, even though none of the fundamental physics has a preferred direction. And if you heat up a magnet enough, the heat will overcome that binding energy, and suddenly the magnetic field vanishes and the atoms are just pointing every which way again. So if you go to high enough temperatures, high enough energies, the symmetry restores itself. It's the same thing with supersymmetry. And so it turns there are a lot of reasons to believe that supersymmetry is almost certainly true that have to do with pure standard modicle particle accelerator physics. I would say that just watching the trajectories of various variables as a function of energy gives us very strong reasons to suspect that certain things are happening up at the higher energy scales, just that certain curves look like they're about to meet. So, when curves start doing things like this, then you tend to suspect that they're going to keep doing that and ultimately touch. And supersymmetry is necessary to make string theory work. It turns out if supersymmetry is false, you can have non-supersymmetric string theories, but it gets a lot weirder. Basically, string theory will work, but it will not predict that you have a universe with dimensions in it, for example. And as far as the current state of it, the state of it is fine. The problem, so there was some really crappy science journalism a couple of weeks ago. There were some results from the LHC that ruled out some corner of the parameter space of supersymmetry. Right? So with supersymmetry, we have, even in the simplest version of the supersymmetry, we have there's a couple of free parameters, like 2 or 3 free parameters. And you can draw a graph of, okay, here are the possible values of it, and this area is ruled out by that experiment, this area is ruled out by that experiment. Well, okay, some data from the LHC ruled out some tiny little region, and some rather shoddy science journalism turned this into, oh my god, supersymmetry is false, all of string theory is doomed! Which is just
Oh, you mean it's not? So when you're actually doing science and trying to be more accurate and precise, the fake stuff is doomed. But that doesn't mean the science is doomed. That means you're actually doing the science.
Yeah, actually, supersymmetry is doing fine. Honestly, our much bigger concern with supersymmetry is that the LHC won't be able to get up to high enough energies and luminosities to actually measure supersymmetry directly. And part of the reason we're sad about this is that the superconducting supercollider, which was a bigger particle accelerator that was supposed to be built in Texas, got axed a couple of decades ago by now, I guess, due to funding cuts. And the SSC would have had a much, much better chance of being able to actually see supersymmetry. The LHC is only about half the power that the SSC would have had.
And just to clarify, LHC is a Large Hadron Collider. It's some of the CERN hangouts we've been having. That's who we're talking about here with the Large Hadron Collider.
Yep. Biggest particle accelerator in the world, under the ground in Geneva.
And you already answered Cindy Brown's question by that, because she was asking what have the recent results from the LHC done to string theory.
Yeah, and the answer is not very much, unfortunately. I wish they would do more. We need more experimental data. But so far, the LHC results, they've been great for finding the Higgs. The rest, well, okay, LHC is still very young. It's only been firing for like a year or so.
Yeah.
Yeah, now, should we continue on more of the 10 topics of that question, or should we move to something else?
Well, we've got about 5 minutes left, and actually I think I'm going to be selfish and do a question for myself, because I'm a jerk like that, and whatever.
You're the producer.
That's right. So my question is, Star Trek, Star Wars, or Doctor Who?
Oh, hard choice.
Yeah.
Star Trek has that wonderful optimism about the future. Star Wars has that wonderful epic narrative scope, the operatic structure. But and Doctor Who, the writing oscillates between brilliant and terrible, but ultimately I feel like Doctor Who got the sense of wonder better than anybody else ever did.
I have to agree.
I'm going to vote for Doctor Who.
I like you even more. This is awesome. Well, just figuring with all those strings vibrating and wibbly wobbly, timey wimey, that makes more sense to me on that end. So I wanted to take time to thank everybody that came out. Sorry we weren't able to get to all the questions out there, especially some of the more technical ones, but I'm sure we will find time later on to have a more technical discussion here with Yonatan. Again, this is the month of December, and stay tuned for many more Hangouts, because it's only the 18th, so we still have a little under 2 weeks left to go with all of these. Again, I'm Scott Lewis, and our wonderful co-host here, Bedini.
Yeah, and if you want to follow Science Sunday for more Hangouts like this, because we will be doing this past December as well, So stay tuned and use the Science Sunday hashtag if you share posts about science. And we trend pretty much every weekend. So that's cool, getting people enthused about science.
Any last words, Yonatan? Your final statement. I'm going to let you have it. I feel like Bill Maher now.
Do science. It's awesome, and you get to find out how the universe works.
It's true. Very true.
Perfect.
Thank you very much for joining us. I know you have a busy day, taking over the world and writing all the apps for everything, explaining the universe to people at 3 a.m. in your free time. So I do appreciate you doing that as well. Everyone have a great rest of the day. Later on today, there will be another December Hangout in about, I want to say 6 hours. The event page is going kind of crazy, but it's the Cosmic Ray Show, and he will be discussing with two doctors. I don't have it up in front of me, but not that doctor from Doctor Who. But they'll be going over the doomsday myths about what's happening today.
The world's going to end.
Oh, right.
Yeah.
So if you search the hashtag December on the event pages, you will be able to find that. And against the Cosmic Ray Show, he works with us over at CosmoQuest, and it will be good fun. So thank you very much, and everyone have a great day.
Yeah, thanks for joining us, Yonatan.
Thank you for having me.
Okay, I'm going to end the broadcast.